Me, everyone. I'm Harry. I'm from the Department of Physics and Astronomy. I'm a postdoc there. So I'm going to run you through quite a broad topic. So we're going to stay quite high level with this thing. But yeah, we're talking about artificial intelligence in searches for new physics at the Large Hadron Collider. So firstly, what is the Large Hadron Collider? Well, it's this 27-kilometer circular particle collider about 100 meters below ground on the Swiss-French border. And the idea here is that we're accelerating particles to 99.9999% the speed of light and colliding them together at one of these four collision points that you can see mapped on here. So I and many of the other people in the room and at Sussex work on the Atlas collaboration. So it's one of these four main detectors, and they sort of act as this sort of 7,000-ton camera that takes a picture of each collision and follows all the particles as they come out from this collision and tries to reconstruct and identify them. And really, a primary goal here is to search for new physics beyond the standard model. Now, the standard model is sort of our benchmark theory. It's arguably the most successful theory ever written. It predicted the Higgs boson's discovery decades before it actually happened. But it has its own shortfalls. You know, we have things like dark matter that we can't explain, matter, antimatter asymmetries in the universe. So really, the idea is we're looking for cracks in that theory, new particles, new forces, or even new phenomena that we haven't even theorized just yet. So here's the challenge that we have. It's a really sort of big data challenge. So at the minute, we're taking about a billion collisions per second. Now, we call these guys events. And each collision itself produces maybe 20 to 25 particles. And you've got around 40 to 60 overlapping collisions at any one instant. So that means that in each snapshot of the detector, you've often got thousands of particles to take a picture of. And you're taking billions of these snapshots every single second. So over the course of 2015 to 2024, the running period that we had, we recorded, roughly speaking, about 30 quadrillion events. So this is, of course, quite a big data problem. And new physics could be lying really in just a handful of those events. And that's obviously incredibly difficult. And that's why you need some sophisticated tools. And to put this into sort of a vague analogy, you can imagine sort of a game of Where's Wally, but Wally is 1 pixel and the book is maybe the size of Europe. And the book is flipping pages a billion times a second. And Wally is sort of a theoretical construct. I tried to sort of generate an image from an AI as to what that would look like, and it sort of put Wally in a higher dimension, which is maybe true. That's maybe fair. That's where the new particles might be. Okay, so I just want to highlight what AI sort of means in our context and our field. So really what we mean is machine learning. We're talking about algorithms that learn patterns from data. And you can sort of broadly divide that into two categories when you're talking about searches for new physics: classification and anomaly detection. Classification is sort of the thing that you use when you have a theory and it tells you what you're looking for. So you generate your signal, you generate your background, and you train a model to sort of separate the difference between them. Anomaly detection, however, is sort of something that you use when you don't know what you're looking for. So the idea here is you train on your background and then flag up anything that the model finds surprising. One is more of a targeted situation, whereas the other is more like casting a wider net. So classification at CERN is actually quite old. It's been used pretty much since the beginning of the previous collider before the LHC. One of the earliest papers that I could find is from 1992 from the Delphi collaboration. So that was doing classification using neural networks to tag different flavors of quarks. So we've had, over 3 decades to refine these techniques, and they really serve us incredibly well, even to today. But classification can only get you so far because it depends on essentially whether the theorists are right about what you're looking for. So if we're searching, we've been searching for things like supersymmetry and extra dimensions for over a decade now, and we haven't actually found anything there. So there's this growing question amongst the community: what if new physics isn't like any of the models that we currently have? And that's really where anomaly detection comes in and shines. So instead of asking, is this event a SUSY event, which is a bit of jargon, is this event sort of weird given our precise understanding of the standard model? Now, anomaly detection comes in sort of several different flavors, and they're not really competing, they're more complementary, and it depends on the sort of signal that you care about. So So you sort of, on the top level, you have your autoencoders, and this sort of asks, right, can I reconstruct this? Can I go from one space to a latent space and then another space? And can I learn the features well enough to reconstruct it? If I can, it's like my standard model. It's like my background. If I can't, then perhaps this is a weird new event. Normalizing flows, however, is more statistical. It sort of gives you a real calibrated probability density. How probable is this event that it is background, it is from my theory, or whether it is sort of a sign of new physics. And then you also have sort of a bit more specific and weakly supervised methods like Quola and Cathode that asks, does this region of data look different than what I would have expected? And the key thing to notice here is sort of the assumptions behind these underlying techniques. So autoencoders and normalizing flows assume that your new physics lives in the sort of outliers of the parameter space. While the other techniques like Quola and Cathode, they're specifically what we would call bump hunts. So they need the signal to be localized in some variable, such as mass, perhaps. Whereas on the flip side here, these techniques are a bit more sensitive to overdensities. But there's no sort of universal anomaly detector. And that's why sort of at Atlas, we use a lot of these different techniques for different purposes. Okay, so with the final minute or so, I'm just going to highlight one technique that's sort of got growing interest at Atlas, and this is normalizing flows. So a normalizing flow algorithm learns an invertible transformation. So it takes your sort of complicated, lumpy data and it warps it into something simple like a Gaussian distribution. So you can think of it sort of like taking a crumpled up piece of paper and unfolding it back into a flat piece of paper, and the algorithm will sort of learn at each point how much stretching it took to take that crumpled paper back to the flat sheet of paper, and that sort of the amount of stretching required at each point you can sort of analogize as being sort of well, quantifiably your probability density of how anomalous this event may be. And how this looks in practice. So there's a recent paper literally published last year. So this uses normalizing flows in sort of a certain region of the feature space. On the y-axis here, we've got our number of events. We're literally counting the number of events in the bins. And our x-axis is this anomaly score, which, and you can sort of see that in the colorful histograms there, that's our prediction from the standard model. And overlaying on that is our data with some uncertainties. And you can see here that even in this high anomalous region of this search of this parameter space, the data agrees rather well with the standard model prediction, which is, okay, sadly, it's no new physics for us, which is, of course, what we want. But it is an incredible confirmation that this theory of the standard model is successful. Okay, yeah, I'm out of time, so I can just skip on the summaries and leave them up there.
Andy has one here. Over. Yeah.
How worried are you about like with the or how worried are people about in the generative techniques about sort of hallucinations and things like that?
Well, you know, so it actually hasn't been, that's a conversation that I hear about when you're talking about LLMs and stuff like that, but I don't necessarily hear that conversation. I mean, anomaly detection is kind of, historically, we've always assumed that the theorists have been right. So we've always assumed that we can search for a specific model. So we haven't, so anomaly detection, broadly speaking, is kind of a new technique. And honestly, it's, I would say, not very worried right now because there's not many conversations about it.
Is a flip it around. Yeah. Do you think there's a chance that it's just the wrong? It's not that it's not there. It's just the wrong maths you're using to look for it.
It's the wrong what? Sorry,
the wrong maths, or the wrong stats,
the wrong
methods. You know, like it could be there, but it's the wrong. No.
Yeah, yeah, and that's sort of why you would use complementary techniques. That's why you wouldn't sort of wed yourself to one anomaly detection algorithm. And the thing is, really the anomaly detection would be a guide in the sense that we would look in a certain parameter space and look for a disagreement between the data and your standard model prediction. And then once you sort of see a significant disagreement there, you would do a like a model dependent search there. So you'd have your theories draft up, simulate your signal again, and you do something a lot more targeted.
Sorry. Yeah, I think you might just have answered the question I was going to ask, which was about your model independence. Do you ever really want it to be truly model independent, given that you have the standard model so well established as a theory? Do you want to abandon that entirely and just go purely data driven?
I don't think so, because like I'm just trying to think about the headlines where it's like, new physics, but we don't know what it is. It's just it just disagrees with what we predicted. I think it'll always be sort of a guiding principle would be the anomaly detection, and we'd always try and then have some model dependence to follow it up.
Yeah, so you're using data that's been collected from tools and instruments in the LHC, and you're looking for anomalies, but how much of the anomalies you would detect and actually seeing just come from noise, just come from bad measurements?
I mean, the thing is about these analyses is they take years to do, and the primary reason for that is the calibration that happens beforehand. So you have to have an unbelievably strong grip on on the predictions from the standard model, especially when you're in far corners of feature space where statistics can vary massively. But we've had this detector currently that we have now for well over a decade. You're talking about one of the biggest collaborations on Earth. We've got tens of thousands of people working on the calibration of this, so we've got a good grip on our noise at the minute. But that question should be always kept in mind, especially when you're in the far corners of feature space.
Yeah, one more.
Hi, maybe naive question, but could you say a little bit more about how you evaluate this model? Because if you say that you don't define a signal for it to detect, how's the training going to work, and how's the evaluation going to work? I mean, how does it know when to say, well, this looks anomalous, if you don't feed it with some label data?
So this is maybe okay. Hopefully, I get your question. But we also use a lot of signal benchmarks to be able to quantify whether the model can actually detect an anomaly or not when we train it. So the first thing that we do is we define sort of regions of feature space where there's only standard model, or at least if it's completely overwhelming that you wouldn't see anything anyway. And we use the actual data from there to calibrate it. And then when we expand it out into other regions, we also use sort of benchmark signal models that have had their own independent search and have been published and are confirmed. So we know they perhaps don't exist. And we use that to calibrate, would we be able to see this or not? And that is the case. This analysis I showed an example for used 4 different signal models and had a competitive sensitivity if that model did exist, but it doesn't. Or at least it's been excluded at that mass range. Does that answer your question?
Okay, I think